look at inferences about means. What I'd like you to do is pause the video and read through the beginning portion of the chapter and pay special attention to the central limit theorem because we're going to be applying that to the examples we use in this chapter. Recall that the central limit theorem says that when random samples are drawn from any population with mean mu and standard deviation sigma, the sample means, y bar, have a sampling distribution with the same mean, mu, but remember the standard deviation is calculated using sigma divided by the square root of n. No matter what population the random sample comes from, the shape of the sampling distribution is approximately normal, as long as the sample size is large enough. Remember that the larger the sample used, the more closely the normal model approximates the sampling distribution for the mean, which is going to be important for us to be able to solve these problems. Based on weighing thousands of animals, the American Angus Association reports the mature Angus cows have a mean weight of 1,309 pounds with a standard deviation of 157 pounds. This result was based on a very large sample of animals from many herds over a period of 15 years. So let's assume that these summaries are the population parameters and that the distribution of weights was unimodal and reasonably symmetric. So therefore, we can apply the central limit theorem. What does the central limit theorem predict about the mean weight seen in random samples of 100 mature Angus cows? So since the central limit theorem applies, that means we can use the normal model. And if you'll recall, with the normal model, we can approximate using our 68, 95, 99.7 rule, which we also call the empirical rule. So what that tells me is the standard deviation of my y-bar sampling distribution is calculated using sigma divided by the square root of n. So here I know that the standard deviation for the population is 157 and n is 100. That's my sample size. And if I divide them, I get 15.7. So that's the standard deviation of my sampling distribution. Okay, so what does that mean? It means that if you take a normal model, which we're applying because of the central limit theorem, we know that mu would be in the center, and mu here is the population parameter. It's the mean weight of all the cows, so that's 1309. And I would add approximately 15.7 pounds to one side to get the one boundary, and then I would add 15.7, I would subtract 15.7 from the other side to get the other boundary. So if I was to add 1309 plus 15.7, I would get 1,324.7. And then if I subtract 1309 minus 15.7, I would get approximately 1293.3 pounds. And I would keep doing that. So I'm going to keep adding 15.7, subtracting 15.7 until I am 3 standard deviations away. So what this tells me, remember, is that approximately 68% of the random samples of the 100 Angus cows would have a mean weight that would be between 1,324.7 pounds and 1,293 pounds. Okay, so that's for 68%. For 95%, I would need to be 2 standard deviations in either direction. So that would be 1277.6 and 1340.4 pounds. And then, of course, 99.7% is 3 standard deviations in either direction. And that would be 1261.9 pounds and 1356.1 pounds. So we can say that, approximately 68% of the Angus cows would have a mean weight between those two values. About 95% of the Angus cows would have a mean weight between those values, and about 99.7% of Angus cows would have a mean weight between those values. And that's it for this first video. Please stay tuned for the next video where we talk about the student's T model.